The second talk of the overview talks today by Stefan Rosswog from Stockholm University. And please take it away.
Okay, thanks a lot for the invitation. And I want to talk about a new development from our side, which is a full GR SPH code. So it's less about real astrophysical results, but it's mostly describing how the method works and just showing some of the very first applications of that thing. So, well, let's maybe just start. So I don't think I have to introduce terribly much about why this is an important topic. So we all probably know about this first double neutron star merger detection. And that was wonderful because we have really learned a lot. Well, gravitational waves, electromagnetic emission was detected, Hubble parameter was determined. We got some constraints on nuclear matter, very strong constraints on the propagation speed of gravity. And of course, one of the things that we're very much interested in is the formation of heavy elements. And the crucial thing is, of course, that we had both gravitational waves and electromagnetic waves. Now, it's really important to understand that essentially all of the electromagnetic emission that we see is coming from just something like 1% of the binary mass. And therefore, understanding this 1% that is ejected is really the key to multi-messenger astrophysics, or at least the electromagnetic part of it. Now, well, as I said, both signals are crucial, and you learn, of course, different things, but they're also produced in very different ways. So for the gravitational waves, it's the bulk motion of maybe 3 solar masses or so. And you have length scales of maybe 10 kilometers. You have time scales of, well, a couple of milliseconds initially. And the composition is relatively irrelevant for the gravitational waves as long as the compactness of the stars is the same. But it's very different, of course, for the electromagnetic emission. There we have just 1% of the solar mass in order of magnitude. But at the moment when the electromagnetic emission peaks, we have something like 10 to the 10 kilometers, and we have a couple of days. And here really the neutron to proton ratio is really crucial for what comes out. And this has also been stressed by Francois just before. And I want to advertise here a little bit, especially if you're interested in the ejector, Lagrangian methods. And just an example, which maybe is obvious to some of you, but probably not to all. And the importance of shocks is, of course, always stressed in hydrodynamics because they are super relevant in astrophysics. But actually, advection is also a very important property, and especially if you're wondering about ejector. And just an example. So what I'm showing in the first example here is just a single star that is set up in hydrostatic equilibrium. And then you don't do anything apart from just transporting the star across vacuum. And you see what's happening here. So the star is, you see it's starting to get a bit deformed. And you start seeing these plumes showing up here. And this is, of course, just an artifact because you have to do work for the advection in a Eulerian method. And of course, you can always argue, well, with good enough resolution, this all goes away. But let's be honest, normally we don't have, well, all the resolution that we would like to have. And therefore, it would be nice to have something which is also good at advection. Now, an example which I think is a very challenging one, and actually more challenging than the one that I've just shown. And this is now just a toy model where I've set up a high density triangle and advected through a box with periodic boundary conditions. And I'm actually doing this with a Lorentz factor of about 70. And you see there's zero deformation of the thing. And this is not a surprise because this Lagrangian method here has essentially nothing to do. It's just advecting the properties that it has on the particles, and it's not losing that. It's just carrying that around. So it's a very simple problem for this method, but it's a pretty tough problem for the other method. Now, maybe just, this is now not related, of course, to, well, to the mergers that are the major point here, but it is a very nice illustration of the power of particles. And this is now an example where you have a black hole, a 10 to the 6 solar mass black hole, and you have a binary system, and I got the initial conditions from Ilya Mandel. It's a binary system of 2 pretty massive stars that are flying towards the black hole and then become disrupted. And this is simulated with a new Newtonian code, but this is for this example perfectly fine, but it's just really to illustrate what the particles can do. And maybe I just start the movie here. So you see now the first star is past the black hole, it's becoming disrupted. The second star is past the black hole, is becoming disrupted. Now I'm at some point zooming out, but this has nothing to do with any computational volume or anything. This is just for the movie, so there is no such a thing as a computational volume. And now you see we are now at something like 50 hours or so, and the stars have been stretched into very narrow spaghetti-like streams, and they, well, since the gas has pressure, they're held together actually by self-gravity in this case, and you see the inner parts are flowing towards the black hole, then go around the black hole, form this characteristic accretion fan that we know from tidal disruptions, while the outer parts are still trying to escape to infinity. And I would claim this is a simulation that is probably impossible for a Eulerian method, but if someone disagrees, please try it. I think it's a very challenging thing. And it keeps going now for a couple of more hours. So now we're getting close to 400 hours here after the disruption. And one thing that I really want to stress here is that we have zero atmosphere or anything. So vacuum is really just vacuum. And if you look now at this volume that I'm just showing here, and you compare the initial stars with that, then the initial stars have something like 10 to the minus 9 of the shown volume. So this is a huge change. And of course, if you would have to fill this with a background medium, then you would be pretty much challenged with your initial stars here. And the punchline here is really the particles can be very, very flexible geometrically. Advection is exact. So if a particle knows this is my electron fraction and there's no physical process that is changing it, then it's just carrying this around without loss of information. You don't have a computational volume, so there's no outer box or anything that you could leave. And there's really no problem with vacuum. It's just vacuum here is just, well, there are just no particles. So coming from that, I want to now come to our new Sphinx PSSN code. And just as a short intermezzo, I just want to say a couple of things about SPH. There have been in the last few years a couple of improvements which have all gone into our new code, into this Sphinx PSSN. And they involve a couple of new kernels that actually make a pretty big difference. Then this method still uses an artificial viscosity, but it uses within the artificial viscosity slope-limited reconstruction. So this is very, very similar to what you do in finite volume methods. And then this already does a huge thing in reducing unwanted dissipation, but you can do actually even better. You can then also make your dissipation parameters time-dependent by various ways, and this works very, very nicely. And if you're interested in the technical details, this is illustrated in those papers here. Now I want to come to our new code, which is called Sphinx PSSN, and Sphinx stands for Smooth Particle Hydrodynamics in Curved Spacetime. And well, it has unfortunately become a relatively complicated thing. But if you're interested in the technical details, they're laid out in those 3 papers here. Well, and the PSSN here is, of course, related to the way how we solve the space-time equations. So our strategy here, and my main collaborator of the dynamical code is Peter Diener, that many of you know. And what we're doing here, we use PSSN for the space-time evolution, and at the moment with fixed mesh refinement, but we evolved the matter with freely moving particles. And that means, of course, we need some coupling between the particles and the mesh. And we didn't want to rely on some existing code or so, so we really started this thing from scratch. Now, space-time evolution, that is what in this community, many of you grew up with this. So we have a 3+1 split and, well, of course, a spatial metric, lapse and shift. And we use pretty much the same equations that are standard for Eulerian methods here. Now, the SPH part, this is also a relatively modern version of SPH and a general relativistic version of it. And there you start with the Lagrangian of an ideal fluid. And here you have the energy momentum tensor. Then you have the 4 velocities. And of course, the metric enters here. And then you can discretize this Lagrangian in an SPH way. And the rest that you do then is pretty much classical mechanics. So you have to choose some variables, but you can calculate the canonical momentum per baryon. And in this particular case here, this comes out as something like a Lorentz factor times the enthalpy times the covariant component of the coordinate velocity. And then you can also get a canonical energy. And these two types of quantities is what we evolve numerically. Now, if you do this, then the evolution equations of that require quite a bit of algebra, but this is laid out in this paper here, for example. And once you have found them, then you find they actually look pretty nicely similar to the Newtonian equations. But of course, there's a difference, and the major difference is, well, we are not really evolving the quantities that we're interested in, but say in this community, of course, I don't have to say much about this. This is very similar to what is done in standard Eulerian relativistic code. So we also have to do a recovery so that we recover the physical variables from the numerical ones. And maybe just also as a side remark, this is quite different from earlier SPH calculations, which had sometimes pretty nasty terms in them, like time derivatives of pressures and so on. And this one here is actually, as I said, the look and feel is pretty much the same as for Newtonian SPH, and that also helps in, well, tools to just analyze the equations, the simulations. Now we have to do, and this is the technically most complicated part, we have to do a coupling between the matter and the space-time. Maybe I can just briefly go back. Of course, if you want to evolve your momentum here, then you see here you have things like a density variable and you have pressures, but you also have the energy momentum tensor involved here, and you need derivatives of the metric. Same thing here for the energy equation. And that means what our mesh needs for the evolution is the energy momentum tensor, which is originally known on the particles, but what the particles need for their evolution is the information about the metric and the derivatives, because they enter in those acceleration terms. And so we have some particle mesh step, and that is actually the most complicated part of this mapping. And if you just start with what for a person with an SPH background would be the most obvious ways to do the mapping, that actually does not work very well. And that's why we went to other methods. And here I've borrowed essentially some very sophisticated kernel functions that come from so-called vortex methods, in which are an interesting concept in applied mathematics. And we have a hierarchy of different such kernels. And the important part here is, of course, that these kernels are not positive definite. And these kernels are wonderful as long as you have a very homogeneous distribution of particles. But the highest order kernels, they don't behave well if they hit a sharp surface, like the neutron star surface, for example. And that's why we have implemented really a hierarchy of such different kernels. And you start with the highest order kernel and check whether everything is fine. If it is, you use it. If it's not, you go down the hierarchy. And in the end, you have a very robust and positive definite kernel, which is something like a parachute where nothing can go wrong. But of course, in a sense, it is like you pick the most accurate kernel that works. And then you have, of course, the other step. You have to map the metric quantities from the mesh to the particle. And this is done with a fifth order Hermite interpolation. And well, the details are laid out in the papers that I've just mentioned before. Now, this is actually pretty difficult, or technically rather complicated. And I guess the most important thing that you would like to know is then, well, does it actually work? And I think, yes, it does. So the first thing that you would do is you start with a special relativistic shock tube test to see whether things are fine. And if, for example, your momentum conservation wouldn't work, you would immediately see this in a shock tube. And the results of a three-dimensional shock tube with Fink's PSSN is shown here. So you see in red, these are the exact solutions, and the blue squares are the three-dimensional particle positions here from Fink's that you see, well, there's actually very nice agreement with the exact solution here. Now I can go one step further, and you can say, well, now let's look at the neutron star. And to just test the hydrodynamic part, let's do this in Cowling approximation. So just freeze the space-time and then set your star into oscillations and measure the oscillation frequencies. And if you do this, then you find these frequencies here, and you can then check, of course, because this is a problem that has been done with Eulerian methods before. And here we find very, very good agreement of the frequencies, really of the order of % or better in these frequencies. Now you can do the next step, which is making it a bit more complicated to see just whether the coupling between the space-time and the hydrodynamics works. And now you can do the same thing, but you also evolve the space-time. Again, set your star into oscillation, measure the frequencies that you find, and again, they agree very, very nicely with what has been found with Eulerian methods before. Now, this is very encouraging. Now, another test, which maybe at first sight may look trivial, but I think it is actually not. And this is we set up a star as good as we can, and then we don't do anything. We just let it evolve and just see how close it stays to the initial solution. And this is what you see after a simulation time of about 10 milliseconds. And this corresponds to something like 14 potential oscillation periods. And if you really look at the center, then you find, of course, a little bit of wobbling. And that is just due to truncation error, of course. But if you look here at the particle distribution of the densities at 10 milliseconds, that is what you see in red. And our initial condition was what you see in black here. And you see, well, it's staying essentially perfectly on your initial setup. And what is most important here is that the particles remain perfectly well behaved. So the surface of the neutron star is, well, it's just as it should be. And it doesn't require any particular treatment. So the transition between the star and the vacuum is not a difficulty for this method at all. Now you can do another relatively challenging test, and that is now you prepare a neutron star on the unstable branch. And if you look at the literature, and it's a very relativistic neutron star with a very high central density, and if you then look at the literature and you just let it go, then the Eulerian simulations tell us, well, if you just let it evolve, then just truncation error alone should set this into pretty violent oscillations. But if instead you give it a small perturbation inwards, then the same star should collapse to a black hole. And we wanted to see whether we can confirm this. And yes, actually we can. So this is the case where we just set up the star and let it go. And you see it starts pretty violent oscillations. And if I'm saying violent, the velocities there are really something like 60% of the speed of light or so that you see. And if you then look at the evolution of the central density, that looks actually very, very similar to what our colleagues in Eulerian simulations have found. And well, these are just a couple of experiments changing the finite differencing order and resolution and so on. So overall, very nice agreement here also with Eulerian methods. Now let's try the next step. Let's say, okay, let's take the same star, and now we give it a tiny little bit of a perturbation inwards. And what's happening then? And here you just see a slice, and I just show the particles here, and you see the star starts collapsing, and then, well, forms a black hole, and we remove the particles here in the innermost bit at extremely low lapse functions here in the center. And again, very nice agreement with what has been found with Eulerian methods. Now we have an additional, well, these are now the first simulations of neutron star mergers that I want to show here. And we start here with the LaGrange library to construct the initial neutron star solutions. But at that point, we're not yet done because we need to translate this into particles. And that is actually more difficult than you would probably think, because you should not just set your particles on grids for various reasons. And I don't think I have time to talk about this. But the particles, you should use ideally equal mass particles, because that produces the least amount of numerical noise. And then if you have equal mass particles, your particle distribution has to reflect the density distribution that is coming from LaGrange. And the way we do this is by a method which I had called the artificial pressure method. And the idea here is that you do something very similar to solving a momentum equation. So you, instead of using a standard SPH momentum equation, what you're doing is you place your particles according to some guess, and then you measure what the particles see as a density, and you compare this measured density with your profile density. And in our case, of course, that is coming from LaGrange. And then you translate this discrepancy in the densities into an artificial pressure. That's why it's called artificial pressure method. And then you move your particles according to this pressure gradient. So it's something like an Euler equation that you're solving that is driven by errors in the density. And that means the particles move into a position where they minimize the error. And this has actually not much to do with GR or anything. This also works just purely Newtonian. And this was a Newtonian study where this was explored the first time. And these are just some examples. You could just say, try something complicated or halfway complicated. Say, just pick those 3 high density triangles, place your particles initially randomly, and then just apply this method. And then you find, well, the particles rearrange themselves into exactly this this pattern that you have set is your profile density. And you can do the same thing for stars, for neutron stars. This is what we have done here. So this is one example where the neutron star is represented with particles just on a hexagonal lattice. And this is one where it is produced with this artificial pressure method. Now you can do the same thing for binaries. And this is what Francesco Torsello has done, a postdoc in Stockholm. And it also works very nicely for binary stars. And again, this is based on LaGrange. Now, we don't have a huge amount of simulations yet, but just a couple of examples. And some of them I want to show here. And they are, at the moment, these are equal mass systems with 1.3 solar masses, irrotational. We have 7 fixed refinement levels, up to 5 million SPH particles. And just to put this maybe into context, the conformal flatness simulations that I'm aware of, they just use a couple of 100,000 particles. So it's actually substantially more than that. At the moment, we don't have much microphysics implemented. At the moment, this is just piecewise polytropes of various nuclear matter equations of state plus some thermal component. And this is just a couple of snapshots from the MPA1 equation of state, just to illustrate how these things look. Now, we can then also extract gravitational waves. And as I said, our space-time part is nearly the same as what is done in Eulerian methods. And what we can do now is we have, on the one hand, we could use the particles just within the quadrupole approach. And just then we can just calculate time derivatives from the particles of the quadrupole moments and calculate gravitational wave amplitudes. But we can also extract them from the space-time. And actually, they actually agree pretty nicely, I would say. At least the phase seems to be very much aligned with each other. But in the amplitudes, you can have, well, a couple of tenths of % of error. But overall, I think it's somewhat surprisingly good agreement between the two. But I think this has been found by Masaru actually also a couple of years before. Now, just some first more astrophysical results. We had looked for those cases that I had said into dynamic ejecta. And we find numbers that I think are very similar to what has been found overall in other simulations. So for these equal mass systems, we find a couple of times 10⁻³ solar masses of dynamic ejecta. We see that soft equations of state eject more material just because they are easier to shock. Say, of course, at contact, they have larger velocities because they're more compact, and they're easier to shock because their sound velocities are smaller. And we also find a high velocity component, and this has been a matter of debate since a couple of years. And I think many groups have seen them in various ways, and everybody is doubting it a little bit because it's a small amount of material that one is talking about, but it seems that probably everybody sees them somehow. And we also do see them, and we find in those cases that we have typically something like 10⁻⁴ solar masses at speeds of larger than 50% of the speed of light. And this could, of course, astrophysically be relevant, because this could lead, as has been suggested by Brian Metzger a couple of years ago, could lead to a blue precursor to the kilonova, because you have unprocessed neutrons that can decay. But of course, you can also do late-time broadband synchrotron emission from this fast component. Now you may ask, are they real? Well, that's maybe a slightly different question from asking, do we think everything is converged? I think it's not everything is converged, but actually I start to believe that these things are real. And part of the reason is that we see very nice distributions of the velocities as a function of radii, and they naturally extend to these large velocities of maybe, well, getting close to 0.8 c or so. But it's not just a couple of isolated particles that then you would wonder, well, is this just spurious numerics or unresolved stuff or so? But I think the details of that, we cannot make strong claims that things are converged, but I think they're actually physically there. Now the question that is natural to ask is, where do they come from? And this is now from the latest paper that we had out just a couple of weeks ago. And what I've done here for this particular APR3 equation of state is I have, at the end of the simulation, I've identified the particles that are unbound, and I've binned them into those velocity bins from blue to red. This is slow, and this is, well, between 60 and 80% of the speed of light. And what we find is that the fastest part here is really coming from this interface between the two neutron stars. And this is the same thing, but now just in Y and Z. And the distribution actually at the very end is actually pretty similar. Is pretty spherical, what we see here. But of course, this may change with different physics. Neutrinos may play a role, and certainly the mass ratio does do a difference here. Now, just to summarize, so this is a new method, still in the early stages of the development, and we have, of course, a long to-do lists on things that we still want to do with this stuff. But I think the basics are working now, and the spacetime is evolved with standard BSSN, and the matter evolution is by 3D moving SPH particles. And this method has passed now successfully many pretty challenging tests. And I would say the major advantage of our method is, well, that the neutron star surface is, for example, no problem. You see here a case, just a snapshot just directly before the merger. And the surface is perfectly well behaved. We don't have to do anything about vacuum. So vacuum is really vacuum. And especially in the context of multi-messenger astrophysics, of course, the ejector evolution is a major point of interest. And I think this will be probably the most compelling advantage of this method, because once the space-time has settled and is stationary, then I think we can essentially evolve the particles for as long as we want. But as I've said, this is still pretty early stages of the development of all of this. And while we have to work more on the code performance, and of course, at the moment, there's not much microphysics in it. But with that, I will stop here, and I'm open for questions.
All right. Thanks, Stefan. It was a very nice talk. And Manuela has her hands up, so let's jump straight in.
Yeah. So can you comment about magnetic fields? I think I might have missed that, but how would you? Yeah.
Magnetic fields is not the most natural thing to include here. So that is the thing to say. And the reason is, one difficulty is, of course, the diff-B constraint, and that is relatively straightforward on a grid, but it's not so straightforward on a particle. But you can do these type of things with hyperbolic divergence cleaning methods, and that actually does work. But the thing that I would say is, in many cases, and especially if we talk about ejector and stuff, one of the major advantages is that the particles go where the mass wants to go. But if you're now interested in magnetic fields, they can, of course, be strong in regions where you don't have many particles. And they're kind of like one of the major advantages of the method turns against you. So you could have regions that are interesting, say a jet, where you don't have many particles. So I would think for magnetic fields, it's not an ideal method. But since we have, in a sense, the particle mesh method, if you really want to implement it, you could do it on a mesh. You could do it like a PIC method or so, that you do it on a mesh. But this would also, well, I think it would not be ideal, because one of the reasons why we went for this method is that we thought if the space-time is not too extreme, then we can probably get away with a relatively low resolution on the space-time side. Say if you have a very stiff equation of state and not too much centrally condensed SAW, you probably get away with not too many grid cells for the space-time, and you can put all your computational resources in the particles. But this would go away if you would want to have a mesh that follows, for example, the magnetic fields. It's probably doable, but it's not one of the first steps that we want to have a look at. So any things you want to do before that?
All right, next up is Philip.
Hi, Stefan. Very nice talk. Just two questions. The first question relates to the vortex methods that you're doing your mapping between the particle and the grid. Can you elaborate on why these kernel functions are necessary, and why not a simple SPH kernel just doesn't work in that case?
Yeah, say for SPH, what you really would want to have is a kernel that is positive definite, because you want to measure your densities just with the kernels. And what you have in a Newtonian context is, well, you have positive mass particles, and then this positive kernel, and then you're guaranteed that you never get a negative density. And it's the same thing here, of course. Say our particles here carry a baryon number, and with a positive definite kernel, you're always guaranteed to have a positive density, and that is what you want, because the equations have terms which contain the density in the denominator. So that's for SPH absolutely what you would want to have. Now, the reason why this is not the best thing to do for this mapping is that you can have a look at how accurate your mapping would be. So you have something like a smoothed version using kernels on the one side, and you compare that to the function that you want to approximate. And if you, well, then just, then you have some convolution integrals. You put in a Taylor expansion here, then what you understand then is, to get this as accurate as possible, you have to reproduce many moments of your particle distribution. And if you, well, you can use this to show that if you want to get this accurate, then you have to have kernels which have a negative part. And that means these kernels, they're very nice, but they have negative parts in them, and therefore things can go wrong. And that is why we need this hierarchy. So you can have, say, if you use one of these, I had shown this, the most ugliest one, which is nice, but say it's this one here. But you see, it's a pretty complicated function. This one has negative terms in it. If you use this just across the stellar surface, then you get a very strong Gibbs signal, a very strong Gibbs oscillation. And that can really lead in the evolution. This can really lead to instabilities and to things that are unphysical and that you don't want. And you have to have a sophisticated algorithm which detects this and uses different kernels as you go to the surface of the star. And this is this hierarchy, or this, well, we had called it a mood method, which is also something, I don't know whether everyone is aware of that exists also for pure hydrodynamics, which is so-called multidimensional optimal order detection, which also, instead of limiting the reconstruction, just tries the highest thing that you can get, and then checks all kind of things, whether they are physically correct, and then goes down, if necessary, in the hierarchy, the most robust ones, which are then in the end positive definite, or in those pure mood hydro methods, it means like you're reducing the reconstruction order and get more and more dissipative. And this is a very similar thing. But the reason is, well, maybe let me say one more sentence. So the reason is these kernels have negative parts, and if you would just do, for example, this test, and this is what, of course, was our first try, that you say, well, we have an SPH kernel, let's try this. But if you do this, then you see it's not terribly accurate, and you see the star starts oscillating and wobbling because it's I would think it's not good enough. And these other kernels do a very good job at this. Sorry, there was another question.
Okay, that's good. So now when you do your pressure part of it and the density estimate for your SPH, do you use the same kind of kernels, or do you use a regular SPH kernel in that case?
There we use. I had very briefly said this here. There's a very nice class of kernels going back to Holger Wendland. And these kernels have the nice properties that in the evolution, they keep the particle very well ordered, and they're much better than the standard cubic spline kernels that people have been using forever in SPH. And this is beautiful, but it comes at a price. If you want to use those kernels, then of course you want a regular particle distribution because that is crucial for your interpolation accuracy. But also you need, for these kernels, you need large numbers of neighbors. So it's not completely free of a computational price. And so I'm not sure what people in cosmology are doing today, but the last time I checked, very often people used for each particle something like 30 or 40 neighbor particles to sum over. What we are doing here is really we're summing over hundreds of neighbor particles, or to be precise, we're summing over exactly 300 of such neighbor particles. And that makes the SPH summations somewhat more expensive. And it also makes, you need to find those neighbors at every time step, makes also this more expensive. And you just have to handle lists of neighbors, and they become much longer, whether you have 300 neighbors that you're searching for or 30. But I think this works very well, but it's not free of a price. So it costs you something, but I think it's really worth all these extra computational costs that you have to invest for this.
All right. Thank you very much.
All right, next up is Wolfgang.
Yeah, hi. That looks very promising. I have a couple of questions. So first, could this be used to study also accretion disk, or would all the SPH particles be basically in the central remnant? Related, have you looked at the thermal evolution? So how much artificial heating or cooling is there? And finally, more as of an outlook question, do you think it would be easier to implement viscosity than for Eulerian methods?
Lots of good questions, Wolfgang. So about the disk, I think one thing that you would probably encounter, say you could do a disk, I think this should probably not be a problem at all. What you would have though is to have exact baryon number conservation, you keep the number of baryons per particles fixed. And that means, well, if you set up a disk, initially, you may have millions of particles or whatever you have set up in the disk, and then you would slowly drain that thing. So that would mean in the disk, you would at some point lose resolution. So it's a different thing than from a grid-based code where you just say, well, these are my grid cells. And if the density goes down, you still have in a sense, the same grid resolution. In our case, you would lose resolution there.
Oh, sorry, I meant specifically for a BNS merger, so where all the matter initially comes from the two stars. Sorry, I wasn't clear.
But I guess if you're interested in such a disk, then one of the key ingredients for the disk evolution would be the magnetic field. And then we're back to Manuela's question from before. But in principle, you can do it. So now the other point with the viscosity is, well, there you would probably need higher order derivatives. And that is something that is probably easier to do accurately on a grid than it is for particles. You could probably also do this, but to have this accurate, you would need to, well, every particle would need to invert matrices at every time step or every substep to get those derivatives. That's doable, but I don't think there would be any obvious advantage if you really want a disk compared to a grid-based method. Sorry, was there another question, Wolfgang?
Yes, about the accuracy of the thermal evolution.
Yes, you mean whether there is heating from artificial dissipation, or what do you mean in terms of thermal evolution accuracy?
Yes, for example, if you would for your isolated TOV test, if you would plot, for example, something related to the specific entropy that should remain constant in the absence of shocks.
Yeah, I think this is working well, although I don't have a very quantitative test of what you're asking. But say one thing that we have implemented in actually the first of those papers is we are not enforcing exact conservation of entropy in the method, but that leaves the specific entropy as a monitoring quantity. So what we have implemented there is we said, well, in an ideal fluid that should be conserved, and if it isn't, then the reason is either there's a shock going through, or maybe your particle distribution becomes noisy. And we have kind of like turned this around, and this is something that is actually also done in Eulerian methods, that you look at entropy, local entropy non-conservation, to choose how much dissipation you have. Actually, I was pointed to this by David Radic in 2015 at our micro meeting in Stockholm, and I've made, where is it? This one here. There's one paper where I tried this in a Newtonian context, and where you see this, the dissipation is essentially complete. But I don't have the plot right here now, but I have such a Rayleigh-Taylor test where you see the dissipation parameter is essentially zero everywhere, apart from the exact interface between the two fluids, the dense fluid and the low density fluid. And so we have used this to steer the dissipation, and that works very nicely. But we have also implemented another way to steer it, and the reason is just if you implement more and more microphysics, then each time you would have to come up with an exact definition of what you mean by entropy. And I don't want to have such a dependence on the microphysics part in the hydrodynamic part. And therefore, we have also implemented an alternative thing. And this looks just at compression. So if you have a velocity divergence that increases in time, so you're compressed and more increasingly so in time, then a particle realizes, okay, I'm moving in a shock now. Now I'm increasing my dissipation. And once the shock wave has passed through, the dissipation decays back to a very low flow value. So I think this is actually pretty well under control. And there are gazillions of such tests in a Newtonian context, but many of those hydro things are actually very similar, whether you do them in a Newtonian context or in this GR context. And many of those tests you can find here in this Newtonian magma paper. And it also illustrates this other thing, how powerful the reconstruction is in this artificial viscosity term. So it's also a very nice thing. Even if you have very big fat parameters everywhere, the dissipation, the slope limited reconstruction massively reduces spurious dissipation.
Thanks.
All right, next up is Udi for the last question before we take a break.
Thanks. It's beautiful code. But I have a very short question related to the previous talk. Can you include nuclear heating during the evolution?
Yes. That's one of the as I said, numerical methods are difficult, and it is some things are difficult in the method and others are very simple. And yes, we can, and that's one thing that we will do hopefully pretty soon. But one of the major advantages is we can evolve the ejector essentially to infinity, and it's very trivial, which probably costs 2 or 3 lines of coding to implement nuclear heating. So that's very simple.
Thanks.
Right, given that was a really quick question, and you said you can essentially evolve the particles up to infinity. Let me ask one really quick follow-up to that. Mm-hmm. Do you freeze your spacetime and then use like an approximate stationary spacetime for something like that? Or would you, because probably don't want to keep on evolving the BSSN equations in that case, right?
No, that's exactly the thing. So it's at some point, this is a pretty good approximation. If you just say whatever is inside, you replace this by a stationary metric. If it's admissible, take some co-metric or something, and then you're just evolving the particles in a fixed spacetime. And then the only thing where you have to be a bit careful is the time stepping, of course, especially if you then include extra effects like heating or so. But these are things where you just have to be careful. But I don't think there's a major fundamental problem that needs to be solved. That's straightforward.
Okay, very nice. So let's thank the two speakers again.